In the context of the A-star algorithm, heuristics try to estimate the actual distance or the minimum cost I need to reach a solution. Heuristics can be consistent. Intuitively, that means that the heuristic will never overestimate the actual distance. Now, why do we want heuristics to be consistent? Well, it's because if an A-star algorithm uses an heuristic that is consistent, then the solution that it gives me is guaranteed to be optimal. We can see why that's very important. One heuristic that is widely used in the 8th puzzle that we see on the left is the Manhattan distance. Why is it widely used? It's for two reasons. The first one is because it's consistent, and the second one is because it's very easy to calculate. So let's do it here. We first identify all the tiles that are not in their correct position. After that, we calculate the distance to its correct position using the Manhattan distance. So in this case, the difference between the Euclidean distance and the Manhattan distance is clearly seen in the 7 and 3 case. We have to move one to the right and one to the left to reach the correct position. And that's the minimum distance to reach it, right? So that is the Manhattan distance. Then we sum all of these distances and we get the Manhattan distance. Okay, that's perfect. Now, there is another heuristic that's called the linear conflict. This one is an extension to the Manhattan distance. That means that it looks at something that the Manhattan distance does not, and that is that some configurations are harder to solve than others. In this case, if we look at the tiles 2 and 1, it's in the Manhattan distance, you just grab 1 and you put it where the 2 is, and you grab the 2 and you put it where the 1 is. Well, that's not how it works in the real life, right? In this problem. In the problem, you actually have to look at the empty square. And you have to use the empty square to move the tiles and to actually switch them. It's very, very hard. And that's what the linear conflict tries to explain. So let's look at the definition of the linear conflict to understand it a little bit better. So the definition says, two tiles, Tj and Tk, are in a linear conflict if Tj and Tk are in the same line. The copositions of Tj and Tk are both in that line. Tj is to the right of Tk, and the goal position of Tj is to the left of the goal position of Tk. Well, that's a mouthful, right? Let's try to analyze it a little bit better to understand it clearly. So the first thing is that it identifies two tiles. So let's just put the two tiles in the puzzle. So let's say this one is Tj and the other one is Tk. So it says that those two tiles are in a linear conflict if Tj and Tk are in the same line. Are they in the same line? Yes, they are. That's true. The goal position of Tj and Tk are both in that line. Are they in the same line? Yes, they are. That's also true. Tj is to the right of Tk. Is that true? No, it's to the left. So that's not true. But if we switch Tj and Tk, something interesting happens. If we switch them, it is true. So that's true. And then the goal position of Tj is to the left of the goal position of Tk? Yes, it is. So those two form a linear conflict. In this puzzle, that's the only linear conflict that we can find. Now, the heuristic is not only identifying the linear conflicts, it's also using an algorithm to calculate something else that allows us to make a consistent heuristic. So the algorithm says, look at every row and every column of this puzzle. So let's look at the first row. Then look if there is a linear conflict. If there is a linear conflict, then you have to figure out the minimum amount of tiles we have to remove so that there are no linear conflicts. In this case, we just have to remove one. So we add this one to the heuristic. Then we go to every row and every column and we do the same. And there is no other linear conflict, so we don't add anything else. Then this amount that we figured out, we multiply it by 2 and we add the Manhattan distance. And that will give us our linear complex heuristic, which is 8. I want you to look at two things here. First, the linear complex and the Manhattan distance are much lower than the actual distance. That is because these heuristics solve a relaxed problem. They do not solve the actual problem. That's why we're using A star. It would be very, very hard. We solve a relaxed problem. I also want you to look at the coefficient 2. This coefficient, the paper that these people made to show this heuristic, demonstrate proof that with 2 here, this heuristic is consistent. Were the coefficient not to be 2 and to be 3, it is not proven that it's consistent. So we cannot use it as 3 if we want it to be consistent. Now, there is something interesting here that I want to point out. If the costs of the puzzle are not the same as the original problem, so in this problem, every movement is 1 as a cost, has 1 as cost. In the case that in another puzzle, the movements are not 1, so for example, there's something called the light puzzle. In that case, the movement for one node to the empty slot is 1 over n. So in that case, it's 1/2. And so on. So 7 to the empty slot is 1/7. In that case, this heuristic is not consistent. And that is very important to understand, because you cannot use non-consistent heuristic if you want to have the optimal solution. Now let's look at some other examples to have it clearer in our mind what the heuristic means, the linear complex heuristic does. So let's look at this one right here. We first have to identify all of the linear conflicts. So the linear conflicts of this problem are this one, and this one. After that, we have to go to every row and every column and look at the row. So let's look at the first row. After that, we look, how many tiles do I have to remove so that there are no linear conflicts? In this case, it's 1. So we add 1 to this initial part of the linear conflicts. Then we go to the next row. This case, we have to remove 2 to remove all linear conflicts. So we add 2 here. After that, we finish all the rows and columns, and we multiply this by 2. And then we add the Manhattan distance, and we reach 12, which is the heuristic of this problem. I want you to solve this problem by your own. So pause this video and then I'll tell you the answer. I hope you got the answer right. It is 24. It's a little bit trickier, this one, but let's go through it step by step. So we first identify all linear conflicts. So here's a linear conflict here, 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 and here. After that, we go row by row and column by column, and we add things to the linear conflict. So the first row, is there a linear conflict? No. Next row, is there a linear conflict? Yes, we have to remove 2 tiles. So we add 2. Next row, is there 1? Yes, we have to remove 1. Next column, there's no linear conflict. And then this column, there's 2 linear conflicts, and we have to remove 2 tiles. So we add 2 here. After that, we multiply this by 2, and we add the Manhattan distance. And you can see that this is 24. Okay, this is the last problem. Pause the video if you want to solve it by yourself. In this case, in this problem, there are no linear conflicts. And that means that the linear conflict is the same as the Manhattan distance, which is the easiest problem we have seen so far. I hope you liked the video, and see you next time. Bye!